One, you are live.
All right, hello everyone. My name is Cameron Grass. I'm an engineer with Power Engineers based out of Hollowell, Maine. I am a substation protection and control engineer specifically. That's my trade. And I will be presenting our protective relaying course, introduction to testing specifically for this presentation. So the other two presenters who I believe are not online, but are easily available for any questions or form of contacts with Power would be Chris Smith and Brian Moores as well. Chris was, I believe, the manager for our testing group for about 5 or 6 years and has another 4 on top of that with testing experience. Brian has many years as a project manager, director of testing, and testing engineer himself as well. Myself, my background actually is 3 years of testing with a previous company, and I just recently moved over to Power to do a more of a design engineering role in-house. So just to get started, a little overview of this entire presentation and the upcoming 2 presentations for next week. We're just going to be going over mainly relay testing associated stuff, including outage preparation, isolation restoration, setting up relay test plans, et cetera, But the PTE group itself actually is responsible for much more than that, including apparatus testing, functional testing, and drawing verifications, markups, and et cetera. So some of the pictures highlighted here is the isolation barricades for relay testing, setting up apparatus testing for, I believe, testing high voltage circuit breakers, functional testing, including wiring checks, functional testing of the relays themselves, and a quick little markup of print over here. So our motto at the bottom here is something that I've recently got quite stuck in my head is do good work, have fun, and make money. That's Power's motto. If we do good work, have fun, and make money all at the same time, then we're doing a good job. So course outline, what we'll be planning to talk about specifically is how we go about planning the work itself, isolation and restoration of the equipment that we identify, preparation and the setup of the testing, and returning the equipment to service and verifying it after as well. Something to highlight as well that is extremely important in the field, and a lot of people will agree with this, is the use of human performance tools. And safety are the main objectives when working in such a dangerous environment. If you think about it, human performance, the way we kind of set up is more or less to identify possible risks and scenarios in which someone or something could end up, in danger of sorts, and identifying those risks and mitigating them prior to anything actually happening. Examples of this would include the use of barricades to isolate equipment that will not be put out of service for testing purposes, the use of PPE, which is personal protective equipment. That includes hard hats, safety glasses, EET423 footwear, et cetera, stuff like that. Because the main motto, especially when you're out in the field, is you want to go home the same way you showed up in the morning. Nobody wants to get injured or worse. And unfortunately, even today, with all these human performance tools and mottos for safety, it still happens. But understanding the risks and planning to mitigate them prior to occurring is the main goal. So to start out, we're just going to be going over some outage planning and one-line prints. I'm assuming you guys have probably already gone over quite a substantial amount of drawings and understood kind of how each one of them works out in the field and what their primary purposes are for. But I'm going to try to narrow this down to the testing side specifically and what we'll be using them for. So some of the objectives for this section is going to be identifying the roles and responsibilities of the testing engineer, interpreting the scope of work, identifying the outage parameters, and identifying the equipment that needs to be tested. So testing engineers' roles and responsibilities, some of the roles that specifically are labeled out here is the testing crew is pretty much the last leg of support to catch any mistakes that could have been missed throughout each phase of the project. Even way back in the design phase, I mean, we sometimes find stuff that, made it all the way down the chain to us, and we caught it in the field doing our physical testing. So it's pretty important for the testing guys to be knowledgeable but efficient as well in identifying any mistakes that may have been made. Verifying the equipment installed properly, working alongside electricians as well. The electrician's primary purpose is realistically just to follow along the prints, identify what needs to be installed and or modified. And our job is to verify that not only they installed and modified stuff correctly, but to make sure and understand that it actually works per design intent. This would include wiring checks, functionals, et cetera, et cetera. Reporting to client for any changes or issues. This is a big one because our primary purpose, besides being safe and understanding the risks and whatnot, is to please the client, because all in all, they are the ones that are paying us to do our jobs. We also, any mistakes that we may find, we usually report immediately to them to identify them, inform them, and make sure that they are okay with any changes that we will be making. And some of the main responsibilities are verifying equipment functions per design intent, not just checking that it matches the prints, but does it actually make sense functionally when it's placed into service? Stuff like that you got to think about. Testing equipment and marking up prints. Again, just marking up the prints is crucial to designate what equipment has been fully tested during the process. Usually this will be done with highlighting the prints to not only show that it has been tested, but to verify that if you were to go back and going along this next line, recording data, to be able to go back after the equipment is placed in service to prove to our client and whomever else that the equipment was tested and functionally verified prior to place in service. Anything like that. This CYA is actually something that I was taught my first year of testing. It pretty much just stands for cover your ass, because not only do you want to make sure that the client is happy with it, but if something were to go wrong, that you can identify where that might have taken place and make sure the client understands that it may have just been an anomaly or whatnot, just proof that you did your job properly. So identifying the scope of work, pretty much it's fairly straightforward. Identifying the equipment that needs to be installed or removed, checking the working parameters and clearances. So this is a big one because a lot of times, especially on a brownfield site, in which case a brownfield is pretty much a substation that had been previously placed into service and had been running for some time, and it is going to be taken out of service, or even just a portion of it, to upgrade, modify, whatnot. Identifying the parameters and the clearances is important so that you're not touching any in-service equipment while you're doing your work, because that can lead to injuries, loss of power to customers, stuff like that, stuff that nobody wants to see. Reviewing outage and energization plans. This is pretty much just a write-up of what needs to take place prior to the start of the job. Understanding that the isolation procedures written up are okay, they cover all your bases, and they make sure that everything's going to be all set once you get into the actual work. And then understanding time constraints and possible troubleshooting tasks. This is a big one too, because usually clients have a pretty strict timeline of when they'd like to get their station back into service. Obviously, time is money to them, and the longer the station is out, the less money they're going to be making, which they won't be too happy with. So identifying the timeline initially, and then again, going back to communicating with the client if you do run into any hiccups, troubleshooting, stuff like that, that may slow down that process is pretty important. So right here we have a one-line diagram. You guys, again, have probably already looked at quite a few of these, but for this purpose specifically, we'd like to just visualize, this is the first leg, especially at a brownfield site, of what needs to be replaced, what's going into service, what's coming out of service for the job, stuff like that. And getting into that is the zones of protection. So right here, we have 145 kV circuit breaker alongside some CTs for protection purposes. And then coming down here is actually the relay one line portion, where it indicates the protection modules that are coming off these pieces of equipment. So we have SEL 451, 411L, 47B, et cetera, going into some lockout relays, some backup GEs, all kinds of stuff. So in this module, we're kind of looking at the zones of protection, in which case for here, we are going to be, I gotta go next slide. There we go. We're going to be indicating which zone is which. So right here, we're looking at the line protection in these green circles. The outermost circle is your primary source of line protection. When you're looking at relay one line, you'll notice that the primary relay is always on the outermost CT of the breaker. And the innermost circle here coming off the secondary CT is actually your secondary relay for your redundant backup protection. Over here on this side, I'm assuming there's more on this side of the picture not shown, but this will be your bus protection side. Again, your outermost circle is going to be your primary, your innermost is going to be your backup. Again, identifying the relays that are actually in your scope. This will be shown here in this blue square. Anything else that may be associated with the protection could still be included, such as these backup relays over here and the lockouts. However, in this application, we're primarily focused on replacing and upgrading this equipment. But when you do go through your isolation procedures, you do want to identify any possible equipment that may be involved in the string of circuits that you're going to be working on. Again, this identifying the 86 lockout relay that would be associated with this equipment alongside probably much more equipment. Drawing review. So when we start a new project, we identify the scope usually through the requests from the client, but we also get drawing requests from them too, to go through one lines, 3-line diagrams, relay one lines, DC schematics for anything that we may be identifying prior to starting the work. Okay, so after we go through everything, the relay one lines are a big one, especially when you're upgrading relays out in the field. Identifying the protection schemes for each relay that you may be modifying. For instance, in this example, a 411L is a primary line protection relay for most clients. It's usually single-ended protection, communication-based tripping, offers reclose initiate or breaker failure initiate schemes as well. Whereas a SEL 451 is your primary breaker control protection. So breaker fail, reclosing, supervisory control, any alarms that may be associated with that specific breaker. And you can see in this example, usually for it, it's been known for quite some time that majority of the time clients specifically use SEL for primary and GE as backup. That's starting to kind of get whitewashed, and we've been getting a lot of work involved upgrading GE relays to SEL, even as the backup relays, just because I believe they're more user friendly in the field, and I think a lot easier to troubleshoot if you do run into problems. But in this example here, you can identify that they have a GEL90 as their line protection for their backup, and their 411L for their primary, as well as the 451 for the breaker.
Cameron,
Yes, of course.
on that previous slide, I'm sorry if I missed it, but what was RI and BFI under line protection?
Oh, I'm sorry. Yeah, absolutely. By the way, guys, if anyone has a question, please feel free to speak up. So thank you very much, Mr. Scott, for speaking up. So reclose initiate and breaker failure initiate are the pretty much those acronyms right there. Reclose initiate is primarily associated with breakers themselves. The reclose initiate function is for a one-off type control for the breakers. So in the situation where a fault may occur, whether it be a tree down the line or something happens on the buswork, whatever, the breaker would open because it sees a fault. If that fault immediately disappears and was just like a one-off type thing, the reclose initiate would actually kick back in. The breaker would close back in, and if it sees good phase angles and proper current and voltage measurements, then it would stay closed. But the other nice thing about the reclose initiate function as well, if that fault does not leave and there's still an issue, when that breaker closes back in, it just trips out and it will not keep closing and opening over and over again. It's a one-time thing. But it is extremely useful, again, for the client and the customer's sake, because if there is a quick fault and that breaker opens, that could possibly lose some customers, and it just kicks back closed, then all's good. So the breaker failure initiate is usually associated with a lockout scheme, where if there is a fault occurring in the BFI circuit, then that can actually trip out more than one piece of equipment. So if there's a heavy feed coming off a transformer side where there's multiple feeders going to different breakers and whatnot, and something catastrophic were to happen inside that circle, that breaker failure initiate could open up all pieces of equipment and save quite a few millions worth of dollars. So.
Okay, thanks.
Yep.
And you can call me Shannon. Thanks.
Shannon, sorry. Yep. So just a quick slide, just kind of going over, again, stuff that you've probably already seen. We got examples of 3-line diagrams, which you can easily identify based on each phase here going in and out of the breaker. This has a lot more detail, especially when it comes to the current strings coming off the CTs, than it would on a regular 1-line. DC schematics usually identify more the relays, any other piece of equipment that may be associated in the control house. This will also show any outgoing contacts coming in and out of the breakers, circuit switchers, et cetera, for high voltage equipment. Panel details for design layout of usually the front and the rear ends to identify what equipment's going where and how it should be laid out. And then relay logic as well. This is primarily for relay testing, automation integration applications, identifying a lot of the how the protection schemes function inside the relay, which I'm sure you guys have gone over with Jude quite a bit. You can probably recognize some of the OR and AND gates. So yeah, this is pretty much an outline of everything I just talked about. So moving on to the outage and isolation plans. So primarily when you're beginning an outage, you need to specifically identify what equipment is going to be placed out of service to ensure that the work that you guys are going to be doing is going to be adequate and it's not going to cause any inadvertent trips or possible injuries, stuff like that. So sometimes weird things can happen. Outages can be sequential, and the client, usually it's for monetary purposes, will only take out one piece of equipment at a time, so that you're not taking out an entire substation or even an entire feeder to customers, because that can also put on a lot of strain on the load for other sites as well. So Sometimes you'll have to identify which piece of equipment needs to come out first, which comes out second, et cetera, et cetera. And then once everything is placed out of service, you need to identify what equipment needs to be tested, whether that be new equipment that they're just going to be placing into service, or if it's going to be upgraded equipment, if you're replacing a relay of sorts, stuff like that. And then restoration time, what would that look like? Is it going to be pretty substantial? Is there going to be, for example, for a new transformer that's going to be placed into service, you actually energize it, and then you have to wait. There's a 24-hour waiting period to let the transformer soak. And then usually oil samples will be taken, tested, and measured to make sure that there was no anomalies during the 24-hour period. Stuff like that should be recognized prior to, so that, you know, nothing weird comes up when the client's asking why everything's not up and running yet. So in this case, filling an outage request, we're going to be identifying the equipment. It looks like this breaker is going to be placed out of service to replace these relays, upgrade them, whatnot. So identifying here how this piece of equipment, or all these pieces of equipment, are going to be isolated. Mainly, the best way to do that is each breaker associated would have these switches shown here that would be opened up, and the breaker itself would also be open. That way no power is flowing through in and out of this circuit, which would also leave the relays to read no currents, no voltages, and have no voltages or currents coming into the control house circuits as well. So that way, when the electricians or whomever go in to isolate and remove the equipment, then nothing's going to be coming in and out. This circle here also is primary fuses coming off this station service to pretty much show that this is how the relays are powered up, and identifying the correct circuit breakers in the control house to isolate those as well is important, because you don't want DC power on while the electricians are in there, because that can lead to, again, injuries, dangerous stuff. So going over some schematic review, test switch operations, this is going to get into the isolation portion specifically quite a bit. So identifying differences in test switches, information contained within schematics, and understanding the order operations for taking the equipment out of service. All right, so FTs, or flexi test switches, I actually never knew what that stood for. We usually just call them FTs. There's quite a few variations of these, and their actually primary purpose is for isolation. It's an easy, accessible break between the relay or whatever other protection equipment may be associated. It's a great break between the relay and the actual circuit going out to the equipment out in the yard, whether it be a breaker or CCVT, et cetera, et cetera. So their primary purpose is for isolation. Usually it's a 1 or a 0 here. If it's open, it's open. If it's closed, it's closed. Current either goes through or it doesn't. The most common that you'll probably see out in the field is these right up here. These are extremely useful for relay testing purposes, especially because it's easy access for these test paddles to be placed right in. You can actually just plug right into, once you open up all the FTs, you can plug right into these top clamps right here, and plug all your test leads in from your test set straight in, rather than having to use alligator clips or anything else for your testing. They do offer other forms of isolation, whether they be stuff like slide links, but you're not seeing much of those anymore, based on they're not super reliable, and can actually lead to injury sometime if not isolated properly. For example, if you're using a non-insulated screwdriver to open up a slide link that has current running through it and it has power on it, if you mess up even just a fraction, you could short circuit the whole thing and cause injury, damage to the equipment, stuff like that. So primarily you'll probably just see FTs for isolation stuff, as well as obvious circuit breakers, stuff like that. If you're looking at the prints, you can identify the test switches usually associated with the DC schematics. Again, their primary purpose is to break the circuit in and out of the relays. So for instance, here this is the relay itself identified right here with its output contacts. You have terminal blocks associated up here, and then you have your test switches to either make or break the circuit. So in this instance, test switch A, which is associated with the out 201 contact in this relay, is actually a trip coil contact going up to the breaker. So if this knife switch was to be closed, this relay was put in service and it detected a fault, this output would close, cause the circuit to make up and go all the way out to the breaker and open to the breaker. If that relay is placed in service and this switch was open and it identified a fault, that output would be made up, but the break in the circuit would not allow the breaker to trip and could cause some pretty substantial damage to the breaker, depending on how aggressive the fault is. Some of the stuff that I can just go through real quick is just identifying each piece of this. So usually this green circle right here is associated with the test switch identifier. This label right here, TS6, would be what you would probably see on the front panel of the cabinet. It also is associated with the cabinet itself, this number 2 here, and the Alpha Echo is, what would that be? That would probably be the panel designation, like where it is specifically on the panel layout that you could identify in the panel front views as well. The test switches you'll usually see out in the field, again, if they're associated with these relays, they'll probably be labeled either 1 through 10. Usually you'll see either 10 or 12 test switches per mounting bracket, or you'll also more commonly probably see A, B, C, D, E, et cetera, et cetera. In this picture right here, you can kind of see how this actually didn't plug in any test switches. It's weird, unless it's under the table. But you can identify all the relays up here and their associated test switches right at the bottom. Has a test set up, is duck ready to go, plugged in. So yeah, I guess all he's missing is plugging into the test switches. So going back to what I was talking about with the accessibility for the test paddles. Once the relay is properly isolated, all these switches should be open. So the test paddle can easily plug in right into the front, and you can easily plug in all your test leads for your current and voltage sources from your test set directly into the paddle, which will go up into the relay and allow you to properly test it. It's pretty easy if you can set it up that way. But again, if it's an older site, especially, and you're going in to test a new relay and they haven't upgraded their test switches, it could be a little bit more tricky to plug in. Identifying the types of test switches specifically, we're looking at the obvious identifier. In this case, it is Alpha, Bravo, Charlie, ABCD, et cetera, and the obvious open close. For AC circuits specifically, it would be more or less common to see your A, B, and C phase voltages coming in to their correlating test switch, not necessarily ABC itself, but at least all gang together in the same block, and maybe your neutral on the other side. It just depends on the client specifically and how they usually come up with their standards. Let's see. In this block right here, you can identify these as current test switches, which again, you'll have A, B, and C. But for your currents, you need an in and an out based on how current flows. It's not like a voltage where it's just measuring off a point. It has to be measured through the circuit. So you'll have an in coming in. Let's say it's coming into this D side, goes up to the relay, and then comes back out E and completes the circuit on the other side. The reason why you can identify these test switches to be current switches specifically is based on this little bracket right here and these shorting bars at the bottom. So for just a quick question, does anyone know what would happen if a breaker was in service and it had an associated CT and that CT circuit opened up? Does anyone know what would happen? Probably.
Yeah, and build up voltage.
Yeah, and that can lead to some pretty big disasters, huh?
Yeah.
Yep. Yeah. Usually on an open CT you can see the arcing sometimes, or probably worse and more frequently than you'd probably expect, but the CT itself can actually just explode because there's nowhere for the current to go. It's building up the voltage like Blaine said. So the reason for these shorting bars is if somehow accidentally or even while testing, I mean, you can damage the relay itself if you have an open CT during testing, but the shorting bar allows a safe path for the current to go if the switch was to be open. Pretty much these shorting bars just lead straight to ground. So again, you don't want to apply a steady, long, strenuous amount of current on these open FTs because you don't want a circulating ground current either associated with this. But yeah, it's pretty much a safety measure, and you can easily identify them when you're out in the field. So yep, shorting tabs, you can identify them if they're closed or open too. Another thing you want to watch out for as well is for testing purposes, sometimes you actually want the CT circuit to be open. And the only reason I say that is because the circuit should be powered down and all you're doing is verifying wiring checks to make sure that everything is correctly laid out based on the prints or whatnot. So sometimes one of the tricks you can do when you're checking these doing wiring checks on these circuits is put a credit card or some piece of paper in between them to break the circuit. That way you're not just, beeping it out all the way through and not really identifying if the circuit's laid out per design intent. So obviously you want to remove the break in the circuit prior to energizing it in any way, shape, or form, but it's just something to keep in mind. And you can identify it with the shorting tabs, whether they're open or closed too. So going back to the 3 lines, like we were just looking at, coming off these CT circuits, you can usually pretty easily identify the relays associated with the breakers and how their current inputs are laid out. So for example, here we got a 21L B2, BL2 451. So your breaker control relay and your line relay, both are associated with this BL2 breaker right here. So primarily it will come off these CTs, go through the relay, have breaks in the circuit, such as these test switches, and can actually go through more than one relay per string. Usually it's not a big deal. Obviously, if you have a break anywhere, it's going to run into an issue, but usually for sake of ease, you can put more than one relay in a string off CTs. So identifying the current switches associated with the relays as well is important for testing purposes. This right here is identifying the shorted currents, meaning that if the test switches were to be open, that it would be shorted actually across past the relay and through the test switch itself onto the next points. So you can identify them usually by these little hook switches here. I don't know if, yeah, these had them too. So it would be a big problem if you were to run into some prints out in the field and they did not have the shorting block associated with the drawings for the relay current circuits. That would want to be marked up, and you'd also obviously want to physically identify it with the panel layouts as well. Where to start when reviewing prints, going through with like the DC schematics. You want to pretty much everything on a DC schematic was there for a reason. That means like all the equipment associated with it, everything, whether it's communication, current voltage circuits, the protection, everything. there is too much to remember most of the time. Every company, every client is different. The way they keep track of all this stuff with DC schematics. My way I always remembered to do stuff was blue pencil for wiring checks. You're just pretty much checking stuff off along the way. And then once you highlight stuff, that means you have functionally verified it in every way, shape, and form that it is going to properly function per the design intent. So your highlighting is the last leg before you give it back to the client and say, yep, it's good to go. So if you didn't test something and you highlighted it, that's on you. That's not good. So in this example here, I'm just going over this print fairly quickly. You got your title block, everything that may be associated, whether it's the revisions, the information, reference drawings that may be associated with any of this equipment, stuff like that. Up here, you see actually a 411L communication board, which is fairly interesting. This would probably, I'm guessing, primarily be used for communication protocols for DTT tripping. And what that is pretty much just a direct transfer trip that is communicate based on Ethernet or sometimes, or a lot of times fiber. That's usually primarily used for station to station communication. And it communicates relays back and forth, whether it's primarily used for the line protection as well. So we got that. Your DC circuit power supply. This is extremely important when you're first looking at the prints, because you want to identify what breaker in the control house is associated with the relay, because it's pretty crucial for making sure that it's powered up when it needs to be, verifying that it's getting proper voltage to the relay, because you don't want to fry the relay. I mean, the things are a couple thousand, $10,000 most of the time. So damaging one of those probably wouldn't impress the client too much. Associated drawings that may go on to other sheets, because a lot of times these relays have so much going on with them that they can't fit them all on one print. Your output contacts, identifying those, it's usually pretty clear because they label them, but verifying that each contact is either supposed to be normally open or normally closed, depending on what the circuit is involved with and how it's supposed to function. Verifying your inputs, anything that may be coming into the relay that would primarily be important, such as output contacts, trip contacts from the breakers, other stuff like that. Any notes that may be associated with it. A lot of times we inform everyone that they need to verify the relay test switches correctly correlate, not only on the prints, but in the station itself, that everything matches up correctly. For instance, going back to one thing that I'd like to mention, remember, so I mentioned the shorting blocks and wanting to put credit cards, paper in those to break the circuit. Well, the reason for that is because if you don't do that and you open these switches, this whole circuit's still going to be made up. So if you reference a point with your meter, and sorry, I'm getting off track a little bit, but you got to do wiring checks when you're out in the field to verify that everything on the prints match up. It's fairly simple. We just take a fluke meter, put it on the ohm setting or the continuity setting, and pretty much just take a reference point and take our other lead and go right down the circuit line to verify that each cable is, or each wire is correctly associated with the point.
Hey, Cameron, can I just add one thing to that?
Yes.
So that can only be done when the circuit's de-energized. So that's probably
Correct.
part of like the initial startup of a place.
Yes.
Because
Yep.
most of the time you can't do functional checks for continuity, because if it's energized, your meter becomes a short circuit and it can cause real problems. So most of the time,
Right.
if you're going through an existing site, you have to do visual checks to verify everything's working.
Yep. Yeah, absolutely, Paul. Yep. Yeah, thank you for mentioning that. It's a big thing. Yeah, you don't want to do continuity checks on an energized circuit, because that can, not only will it just not work, but it can actually damage the meter too, depending on the setting. So going back to putting the brakes in these circuits, especially with the current circuits, it's all about flow, how it goes in and out of each relay. So if you were to break the circuit here and here, you can specifically identify that 2TT1 goes to 0.10 on test switch 7. It doesn't, if it goes to 0.9 on test switch 7, that's a problem, because that means the test switch is actually backwards and won't properly short the circuit out if it's opened up and energized. The same thing too, if these points are swapped on the relay, that's going to read current going 180 degrees out from where it's supposed to be measured, which is going to be a big problem, especially when you go to energize and the client's reading currents that are just way out of whack. So being able to identify these prior to and coming up with a good plan for taking your measurements, wiring checks, functional, et cetera, is very important, especially before you even start the project. Thing I want to mention, what we got here. So more identification stuff. This right here, just identifying the relay type. In this instance, it's 411L, identifying that this is specifically the inputs and outputs section of the board and all the stuff that's associated with it. The panel designation is usually this top two right here, and the panel position would be the AC. A unique identifier is something that differentiates from client to client. Usually they have a set standard, but in this case, I'm assuming they're identifying this as a line relay with their 21L, and B2 could be a backup relay, possibly. I'm not sure what client this is, but each client will have a different identifier, and it can be a little bit of a pain to differentiate them, especially if you're working on different projects here and there quite frequently. Same thing here, 2AD, TS stands for the test switch, and number 3 for the position designation on the panel. Same thing here. This is the same panel, panel 2. TB stands for the terminal block, which is usually the outermost section of the panels for stuff to come in, such as cables from outside equipment going into the cabinets to any devices. And you can actually see it here, jumping from panel to panel 2. So you can go from 2 to 5 if there's associated protection logic in this relay going to the lockout, for instance. So this 52.1, which one is this? I have no idea. So I guess it's supposed to be, oh yeah, it is breaker contact. Sorry, I didn't see the A there. So this is identified as breaker contact, normally open, and it's obviously the primary input for designator whether the breaker is either open or closed in the relay. This one right here, this is again kind of the same idea. It's in this case though, it's actually a lockout relay that's associated with it, identifying whether the lockout is actuated or not. For the wiring diagrams, this is a great print for troubleshooting purposes. It's extremely useful for identifying stuff that may differentiate. So usually the electricians will be working off of these primarily when they're putting in new equipment, new cable, new wiring, whatever. And our job is to work off of the DC schematics because those functionally represent the protection scheme and the design intent properly. But if you run into something when you're doing wiring checks or functionals, this is a great print to go off of to verify whether the DC schematic is off or the wiring was actually incorrect and the electrician just improperly installed it, stuff like that. Again, your title block, any drawing numbers associated, designating the type of drawing, and et cetera, et cetera. So looking at these, you can see usually the wiring, I would say like 99 times out of 100 would be viewing the panel, excuse me, from the rear side. and identifying which side for which terminal blocks would be associated with it, whether it be the right or the left, and all the equipment in the back side of the panel. Determining on these wiring prints as well, which side is external and internal. It's usually fairly straightforward. The internal stuff is associated with primarily just stuff that's going into the cabinet, whereas the external stuff is going to have cable numbers, designations, what type of conductor. In this case, up here, this would be for conductor number 10 with 2 spare wires, number 19, and cable designation, et cetera, et cetera. It's an example right here of what the back of some of these panels look like. This is this is fairly interesting. So I guess this client has an open design cabinet layout, which I'm not the biggest fan of, because I feel like there's a lot of room for human error, especially if there's site visits or any sort of maintenance testing, because there's a lot of bits and ends that are sticking out that could easily be, just simple, like if a wire wasn't screwed in properly and you kicked this bundle right here and that wire got pulled out, you could initiate a trip, you could cause all kinds of issues. So usually
electricians love this stuff because it's
Oh,
so
yeah.
much easier to work on than an enclosed cabinet. They,
yeah.
if you ask them, they would say this is a dream.
Oh yeah, of course, absolutely, Paul. Yeah, because the alternative is usually single cabinets, which aren't exactly the most spacious when you're the electrician installing all this stuff. And design engineers love to cram as much stuff in as they possibly can. So moving on to what is it? Identifying the wiring from the DC schematic to the actual wiring diagram itself. So say you have an issue here between the power supply of the relay and the associated test switch. So in this case, it would be the Z30 contact on the back of the relay going to the test switch number three contact. If you had issues there, obviously you want to identify each piece of equipment to begin with, where the issue might be, and then move on to the wiring and identify it there. So as you can see, you can identify the test switches here, ADTS3, ADTS3, and the relay associated with it would be this entire block right all around here. So again, identifying the points, Z30, if you're looking at this relay, you can kind of follow along to see which block is associated with it. So we have the Z block here. If we go all the way down, you can see that it is actually, in fact, the negative side of the power supply, this number 30. And then going down to the test switch, you can see the B number 3 there. This can get a little confusing if you're going down a pretty large rabbit hole of troubleshooting, but all in all, you just got to associate the contacts from the relay to where it's going. So in our case here, we got the Z30 contact, and that should be going to 83. And if we go down to 83, we can see that, and it is in fact going back up to the AC identifier here, Z30. So going into the process of isolation purposes, this is a big portion for start of an outage. We got to identify what equipment's being taken out of service, what equipment is being taken out of service in what order, and how we're going to go about doing that. So for example, let's say we're going to remove this breaker out of service from this string. The first thing we'll probably want to do is open the breaker itself. And that will break the string of circuit here on this bus work. Oh, I see. Oh, okay. So I'm going to change the subject, change the topic real quick, and I'm going to ask people what would happen if, let's say we haven't even started the outage yet, didn't isolate anything, and we decided, all right, first thing we're going to do is we're going to pull the fuses to power up these relays. So pretty much we're going to kill the power to all these protection devices that are associated with all the equipment on this line. What would happen, do you guys think? just turned off the relays pretty much.
This is a guess, but would it trip the breaker?
Yep, probably would. Yep, 100%. Yeah, so if your protection devices that are specifically there to operate this breaker when it needs to, if that device lost power altogether, it would assume that the breaker just shut off. We lost all power to the site, and that thing needs to kick open. So, yeah, powering down these devices first is definitely not the right step. So in our case specifically, the order operations for the high side of this string right here would probably be to open up this breaker, open up each of these motor operated switches to completely and utterly isolate this entire string of CTs and the breaker itself. Because if you were to just open this breaker up, there could still be some sort of floating current coming into these CTs when working in the cabinets as well. So it just leads to more risks, and it's better to isolate the entire section itself with these switches. And then after all that was done, and we went through our proper isolation steps for isolating the relays themselves, which I'll get into in a second, then you can pull the fuses to the breaker and remove the relays out of service completely. So identifying, we haven't looked at these yet. So we looked at the current circuits, but we haven't looked at the voltage circuits for those relays. But this is a example of the set of PTs coming off the high side going into the relays, and each of them that are associated with it. So again, it's pretty self-explanatory, but you got voltage coming off of the low side, goes through the relay and grounded back out and back on the PTs. So each of them have an identifier for each phase. So you got your A phase, your B phase, your C phase coming off of each one of these PTs. So this is, I believe it's the last section, but this is probably the most important for your job physically at the start of a project. We've gone through all the print stuff, all the markups, all the identifiers and everything that we need to do, but what happens after everything is like all set up and squared away? We gotta, if we're going to be replacing a relay, upgrading it, modifying it, whatnot, we need a process for isolation. So pretty much what that means is you need to come up with a set of steps to properly isolate the relay to avoid any inadvertent trips to other equipment that may be associated with that relay. Pretty much what I mean is if you just pretty much shut off the relay, like I said, it wouldn't only open up this breaker, but there may be a lockout associated with it that could open up another bunch of breakers and maybe even just shut down the whole site itself, which is a big no-no. So our job is to identify the order operations for isolating the relays themselves to avoid any stuff like that. And it actually does apply to lockout relays themselves as well. Did I lose you guys?
No, we're still here.
All right. So in this case, let's see. Show a. All right, so for this example, it's a standard practice that you learn in the field for isolating and restoration purposes that pretty much the first thing you go to is the relays themselves. Look at the DC schematics, identify all the outputs, inputs, currents and voltage areas, and go from there. So firstly, your first step is to identify any trip outputs from the relay that you're going to be isolating. So in this case, we have a trip TC1 for this breaker BL1 that's associated with the 201 on the relay. So your first step is to isolate this trip completely by opening this test switch. That way, so the reason you do your trips first and not anything else is because this is your primary form of completely messing up and operating the breaker inadvertently. So if you say you were to pull all your voltages first from the relay, well, the relay sees no voltage. There's got to be a fault on the line because it's still reading current going in and out. So let me open up the breaker. Well, you don't want to do that yet. You gotta properly isolate it. So you start with your trips. Your breaker failure initiates, like we discussed earlier. That will be your second step, and any other various outputs that may be associated with it, whether that be alarms, communication trips as well. They can have physical contacts coming out of this relay. That would be going back to the communication-based tripping devices. And then you finish out all your outputs before you move on. So once you get all those isolated, realistically, there's no way that this relay can directly cause an inadvertent trip to any devices. Again, there may still be communication-based tripping that's not associated with a physical output, and it could be just all internal stuff on the relay. So that's why we follow these steps to a T. So after your outputs, you'll move on to your inputs, which would just be all associated stuff that may be coming into the relay and may not necessarily have anything to do with the internal logic that could cause an inadvertent trip, but a lot of times there can be, especially with this 52A contact that could be coming from a different breaker. And if it sees that drop out at the incorrect time, then it could cause an inadvertent trip elsewhere. So outputs and then your inputs. And then let's see how this out here, because there's a lot of odds, bits and ends that you may see from time to time. So I just like to see what he has laid out. So your DC trip pass, yep, good. Communication pass. Test modes, again, you won't really see this unless you're working with GE specifically. They're usually the only ones that I've seen that have been equipped with it. I'm sure there are other brands, but most of the times it'll be SEL, and I haven't really seen a client either that uses the test mode for anything. So I don't necessarily agree with this either. I believe powering down the relay is your absolute last step before taking it physically out of the cabinet. I learned that you want to do obviously your trip outputs first, any other outputs, your inputs, and then move on to your currents and voltages. Again, if that relay gets powered down and it's still reading stuff, it could cause issues.
I think sometimes they do the AC current and voltage because sometimes there are fault detectors or sometimes there are under voltage elements that would operate.
Okay.
And so maybe that's the reason why they want to remove the DC power, because it might trigger an events report or something like that. I'm just guessing. I don't know, but that's
sure.
I'm just curious if that's the reason why.
Yeah. No, that's a good point, Paul. I didn't think of that, but again, I've never really seen it before. So, so here we go. Oh, this is the restoration stuff. So yeah, in this case, the main thing is identifying your trip outputs, isolating those first, and then moving on to the rest of the equipment and finishing out with your currents and voltages. And then once your relay is properly isolated, you've powered it down completely, whether it be the AC or DC sources. You should be fairly confident that once you've done all your voltage checks and everything, that the relay is completely powered down, the electricians can get in there and get to work, whether it be replacing it or just taking it out completely. And then the order of restoration is fairly important as well, because you need to do that pretty much the complete opposite end back. So you want to start with your AC current and voltage sources, powering it back up. And then the biggest key factor is once that relay is powered up and it's reading AC current and voltage sources that should be from an energized circuit, you'd want to go into the relay and verify that if there's any standing trips, you don't throw any of the test switches in to continue, because that could cause an inadvertent trip. You want to identify why would there be a standing trip? What could this mean? Why is it there? And troubleshoot until it's been resolved, and then continue on with your restoration process. So doing your communication paths, checking for trips again. You want to identify that there's no standing trips all the way up until you actually put in the DC trip paths. And if you make it all the way through, put all your stuff back in, tell the client the relay has been restored and that the outage request has been fulfilled and the equipment is in service permanently. Once that's all squared away, usually the client will request a physical measurement as well as a screenshot of the relay reading currents and voltages, phase angles, verifying that there is no standing trips, that when you guys put it into service, it was working properly. That way, if something were to happen, like when you leave the site, it worked when we left, something must have happened, whether it be a fault or whatever. So again, going back to covering your ass, making sure that you verify everything works properly. So that's all I have for this presentation, Paul. I got plenty of time for questions if anyone has any. If there's anything you guys would like to go back and discuss, I'd be more than happy to. Just like to hear your thoughts.
I would assume too that Cam would also be open to what's it like for a junior engineer, because he is I believe he's the youngest presenter. You're younger than Jack Conant, right? You've been more recently graduated than Jack, is that correct?
Yep, that is correct. Not by much, but yes.
Yeah. Jack Conant did one of the presentations for power.
Oh, he did.
Back on I think it was AC elementaries and schematics, and so Cameron has been working. Well, he graduated. You said 2019, is that correct?
Correct. Yep.
So you also, for those of you who are interested, you can also find out like what it's like to be a entry-level engineer and, kind of living the life on the road.
Yeah. Yep. Yeah. I'd be more than happy to share any information or
and then
tips
also
that you'd be curious about.
Things to be successful too. Like what are, that I think maybe that would be a good starting question is, what does it take to be successful when you start out as an engineer? We don't know a whole heck of a lot, and there's a lot of things happening. So maybe you can share a little bit about that.
Yeah, absolutely. I mean, me personally, it's a substantial step leaving the classroom and going out in the field specifically, because right out of school, I did do a 3-month training course for testing commissioning with TRC prior to graduating, but that was mostly in a controlled environment, which in this case it was a relay testing lab that they constructed down in Pennsylvania. So it was great to get that information prior to actually going out in the field, but there's really no comparison when you walk onto your first substation and see how big the equipment is, how substantial like everything is, and just kind of makes you look back and think like, wow, that was a lot easier just being in that little office space. But no, it's I also personally think that working in the field for a good chunk of time is the best way to learn. Being able to learn how to read prints, identify equipment on the prints, associate them with the physical equipment in the field is it's a pretty sweet one up on some of the guys that may take an office position right out of school, because you get to see how this stuff physically works and verify it functionally and understand the background of why certain protection schemes may be implemented or why certain types of equipment are used over others. I think it's really really neat to be able to identify that pretty early on in your career and understand it. Like me and Paul were talking about as well before you guys jumped on, but financially, I think the benefits are pretty substantial as well. There's a lot of opportunity for overtime, getting to work on a bunch of different projects, maybe across the country, across New England, wherever it may be. Like I said, a lot of clients right now they're upgrading the protection schemes. Usually it's on a 6-year basis, whether it's just for maintenance or whatnot, but you're never not gonna not have work as long as you're doing it correctly, safely, and efficiently. There's never not going to be work for you out in the field. That's for sure. So.
Yeah, and Cameron also talked a little bit about when the class officially started, that he no longer is in the field, or maybe you are a little bit, but it also can get tiring being out in the field where you're never home. I mean, you're gone for, and Power and TRC are both really good about, having reasonable expectations of saying you're gone for a week or two, and then you're back. There are other outfits that you're gone for months on end. And it's very difficult to have a life that way. So I think Cameron, this is what I really appreciate about Cameron is Cameron realized that what he was doing was interesting and fun and exciting, but it really doesn't support any life outside of work. So I don't know. Correct. That's a valid statement. I don't mean to put words in your mouth, Cameron, but I
not at all, Paul.
That's really important.
No, you're actually right on the money. That was exactly what happened with me. The monetary benefits were excellent, but it didn't outweigh the fact that it was very difficult to have an outside social life, being away from home constantly, being away from friends, family, girlfriends, fiancés, wives, kids, especially. I mean, I couldn't tell you how many, not just like testing engineers, but like electricians, construction guys, I would work out on a project in New York and I'd meet like 30 people from all across the country that have families at home waiting for them. And we're on like a 3 to 6 month project too at a time. And they've been doing this for years and years and years. So I can't imagine like how difficult that must be for them. Some of them like it, which it's all about what personally to you is more important, whether it be a balance of social life, whether it's I need to make some fucking serious money right now and I can do this for a while and then, settle down or whatever it may be. It's just, I think you really should think about all that stuff prior to making a decision. But obviously there is a lot of pros and cons that go each way for sure.
And Cameron, from when he was a student, he was a pretty healthy and fit guy. And being out on the road, it's not always conducive to a healthy lifestyle. Because you get out of work and the only entertainment you have is the bar and a really large meal. I don't know if you want to talk about that at all or.
Sure. Yeah, absolutely.
That was my experience. I saw a lot of guys get trapped into this, get out of work and go drinking and pigging out and rough day the next day.
Yep. Yeah, a lot of guys live their day-to-day lifestyle like that. Especially, I mean, you're working sometimes 6, 7 days a week, 10 to 12 hours, not much free time to go on a hike or go explore or do whatever. You're there for work and that's the primary focus. So the mix of balance when it comes to a healthy lifestyle is fairly difficult. For me personally, though, I found that I would rather make sure I'm healthy as an individual before work. So I managed to stay in pretty good shape. Having a Planet Fitness membership is fairly easy. You can go anywhere and there's probably one within a 30-mile radius unless you're out in the middle of nowhere. Designating certain meal spots, sometimes you can be in a town where they have plenty of great restaurants with some really healthy choices, but a lot of times too, you're out again in the middle of nowhere. And I know one of my coworkers was telling me he worked on a job up at Lost Nation, New Hampshire, and the closest food source was a Subway that was 5 miles away from the site and nothing else. So he lived off that for a few months, and he said that was awful, which I don't blame him at all. But so yeah, it's again, you can make it work. And I've seen, I talk a lot about guys I've seen that struggled with that lifestyle, but a lot of guys, they can manage it. They're pretty good about taking care of themselves physically and mentally alongside getting the job done at the same time. So it's definitely a balance.
Any other questions for our presenter? Really very valuable because you're getting a junior, relatively speaking, junior person with a lot of good experience. So very unique opportunity.
Are any of you guys thinking about going into the field at all? Has anyone even thought of it? Or is this the first you're hearing of it?
Well, what do you mean by in the field?
Testing, commissioning, engineering. Structural engineering. I'm Not sure. Are you guys all EET or do we have some ECE in here as well?
We
I'm
have some-
I'm ECE,
Yep.
and I'm actually working at some power plants nearby already. I wired
Nice.
up a relay today. Yep, to turn on a break.
Beautiful. Awesome.
Yeah,
Yeah,
this class, we do have some industry professionals as well, so.
Yeah,
Go
I
ahead,
was-
Blaine, I'm sorry.
no, yeah. So I was just gonna add that, because I did a little bit of traveling, mostly just around New England, so I didn't have to fly anywhere too far, but
Yep.
it can be a lot of fun.
Yeah, sure.
To go visit bars, and then when you're visiting a bar for a week, usually they got trivias and you meet locals and stuff like that. So, I met a Canadian Olympic softball player one night.
Nice.
So it's like you get stories to tell and stuff like
Sure.
that. But it can be fun for sure.
Absolutely. Yep.
I like to say work travel is fun 1 or 2 days a year.
I'm with you now on that. Yeah, it can be it can almost kind of be a vacation ish, but when you're doing it constantly, it definitely doesn't feel like it. So
Okay, any other last minute stuff for Cameron? All right, well, thanks everybody very much, and we'll see you folks on Tuesday. Have a great weekend.
thank you guys very much.
Thanks.